Well, all right. Here we are. Go ahead and I've got the same audio track playing twice here. OBS. Let me go ahead and take care of that. Well, hello, everybody. We are ready to go ahead and do some live coding this evening, which I'm excited about. And, of course, it is .NET and Scotch night, but I have to begin with an apology to everybody. The whiskey I will be drinking tonight is, in fact, not Scotch. It is a wheated bourbon, and it is a wheated bourbon from Colorado, which makes it an even poorer substitute for Scotch. Not that I have anything against Colorado, but because bourbon has historically been a Kentucky thing, although everyone claims they make it now, so including the state of Texas, where I currently live. So, I'm going to go ahead and begin by wheeling this out. We're going to go ahead and drink. Hello, him Jay, how are you? Is the music too loud? I decided I wanted to pump the jam tonight. Alright, well, before I get too excited and pour this out, in fact, the cap is actually one of my favorite parts about this bourbon. This is Old Elk. So Old Elk is a craft distillery based out of, I think it's Fort Collins, Colorado. It's where the Air Force Academy is. And this is their 5-year-old blended wheated bourbon. So wheated bourbons tend to be a little bit more on the sweet side. Pappy Van Winkle, which is probably the most coveted bourbon of all, is in fact a wheated bourbon. So is Weller and a couple of other well-known ones. So I've already done some damage to this bottle, even though I didn't get it all that long ago, but I like it quite a lot. So I'm going to pour myself a little dram before we start talking about .NET performance and benchmarks. Now, how is everyone else doing tonight? Hope all of you have something good to drink. Alright. Let's go ahead and give this a try. Yep. Has really good sweet notes. It's aged in a relatively cold climate up in Fort Collins, so it's able to go ahead and have a smaller, what we call angel share. Angel share is the amount of alcohol that evaporates during the aging process. So it's one of the reasons why it's a lot easier to find old Scotch than it is old bourbons. Bourbons typically made in extremely warm climates where a lot evaporates right away. Scotland, on the other hand, is very temperate, so it's much easier for them to age whiskey for up to, well, oldest one I've ever had was 52 years old, but you can age whiskey pretty regularly to 12, 16, 15, 18, 20, 25 years and not lose very much. Whereas a 20-year-old bourbon is pretty rare because so much of it evaporates. This is 5 years old. Really sweet. I can taste the oak on it, and overall notes taste a lot like caramel, a little bit like baking spices. All right. So what I have in front of me is some of the work we did on Tuesday night stream. So if you didn't watch, we have the highlights on the Twitch channel. But one of the big things we did is we're working on what we call read side performance optimization. So if I had to go ahead and draw a little diagram of what Akka.net's performance looks like, in fact, I can go ahead and do this real quickly. So I'll go ahead and fire up Smart Draw. It's a diagramming tool that I usually use, and this is what I use to draw some of our Azure drawings from last week. So from a performance perspective, over on the left here, I have Actor System 1, and when Actor System 1, we'll go ahead and click on this, receives request to message actor located at Akka at TCP, cluster sys at localhost 1002/user to this is what, in fact, let me go ahead and make this a little bit bigger here. This is sort of what a full actor path kind of looks like. This little bit down here. And we'll say Actor System 1 is hosted on a different address. We'll say it's port 1001. All right. So when we receive a request to message that actor located at this system, we have to go ahead and establish a connection. So this opens a TCP socket. And then we have to go ahead and serialize message plus addressing information. The actor who's going to ultimately receive this data on the other side of the network is going to need to know who sent it. And so we need to go ahead and incorporate that into our payload. And so then we're going to go ahead, transmit this over the network. I'm going to go ahead and violate one of the rules of flowcharts, which is they should always basically go in the same direction. But since I'm trying to fit this all on one page, I'm going to go ahead and do a loop. So, message gets received and framed by the read side endpoint. Framing a message isn't something we're going to get too much into tonight, because that's kind of more of a low-level socket thing. But basically, we append some headers to the front of each message to let the reader know how many bytes you can expect for this message. When you transmit data over a socket, it just shows up as a series of bytes, and so it's kind of up to the developers who are using the socket protocol to determine what do those bytes mean. And so the first thing you have to usually do when you're working on a low-level sort of socket protocol like that is you have to define a framing format. This is a way of essentially delineating multiple messages all inside that same byte stream. So most people tend to use a technique called length frame encoding, which means I add a header that's a fixed size. Usually it's like 4 bytes. to the front of my message that basically says, here's how many more bytes you can expect after this one. All of those bytes are all part of the same logical message. So the socket may not receive all those bytes all at once. It might have to wait for a second read operation, and that's called a partial read. And that's one of the things that can result in like data corruption and other stuff if you don't have good handling for it. That's what a framing protocol kind of allows you to do. So the framing is already handled for us by a piece of infrastructure that sits underneath Aki.net. We have to deserialize the message. This involves poking into an envelope that contains our addressing information, and it also contains the underlying message payload. So we actually have to perform two-stage deserialization. Deserialize the message envelope. Then we have to parse the, let's say, recipient and sender address information. This is what, let me go ahead and add a couple more little bits here. Now I'll go ahead and fill this shape in real fast. This is what, let me go ahead and change the font color too. This is what we did on Tuesday, was we made this a lot faster than it used to be. And I'm actually going to go ahead and show you in one of our sort of high-level benchmarks just how much faster we made it. So this is what we were solving last week. This is what we call the read side optimization. And then we actually have to go ahead and dispatch the message. Yeah, dispatch message to recipient. This involves traversing the actor hierarchy to some extent. And then finally, if I go over here, I was afraid of that. Let's see if I can go ahead and change that back to this style. That'd make me happy. Okay, perfect. All right, and then actor, DQs message from mailbox and processes it. So our fundamental performance issue is that we need to go ahead and make it so, by the way, it may not just be one actor doing this sort of round trip here. There might be hundreds of thousands of actors inside Actor System 1 trying to communicate with hundreds of thousands of actors in Actor System 2. And it's all going over this one socket connection. So we have to be able to make sure that each of those socket operations individually are really fast. Part of the reason why is because it's all going over one TCP connection. That bit of code that's parsing the recipient and sender address information has a maximum degree of parallelism of 1. You can only go ahead and parse whatever set of messages were given to it at any given time. There's no way for me to go ahead and safely scale that number up or down after we... Well, actually, let me take that back. Only one actor can start deserializing these envelopes. We could, in theory, parallelize this part. But what we've done so far is we've just made that one part extremely fast. Now, the area where I want to try to focus some of our performance optimization tonight is I'm going to go ahead and fill this shape in. We want to go ahead and try to improve the right side of our performance. Now, one of the things we did in Aki.net 1.4 is we actually improved this bit of code, the transmitter right here, to use a smart batching system where it could go ahead and take bursts of messages that were all written in rapid succession and group them together in one go over the socket. So that gave us a gigantic boost in performance for Aki.net. But the next area we want to go ahead and take a look at potentially in terms of trying to improve our underlying performance is we want to go ahead and see, can we make it less expensive to serialize these messages and encode some of this addressing information? So the serialization piece, that's really difficult to handle because a lot of it is really application specific. We can work, of course, on a polymorphic serializer like JSON.net, system.text.json, or Hyperion, or something like that. But we're mostly going to focus on trying to improve the speed at which we encode the address information, because that's something that's fairly uniform for every single actor. Every actor needs to do it. On top of that, on the read side, we actually benefit from caching down here, whereas we don't up here. I always have to go ahead and serialize these URLs every time we do it. So we're going to go ahead and try to get creative and see what we can do to reduce the overhead of this and hopefully improve the end-to-end Aki.remote throughput of our system. Now, I'm going to go ahead and pull up. If you want to follow along with me here, so here's the pull request we worked on last time. It's not merged in yet because one of the other core developers in Aki.net found some address parsing bugs that would result in our code throwing, I think, a Stack Overflow exception. Or not a Stack Overflow, address out of range exception. So we've got to fix that before we can merge this in. In fact, I might actually go ahead and do that first tonight. But if you want to follow along with the big macro benchmark I'm going to run, let me go ahead and drop a link to the Akka.net project in chat. By the way, we finally got around to adding a proper About section on my Twitch profile. So there's links to Akka.net stuff everywhere in there. Although I just realized just now, I actually didn't link to the Akka.net source code. I only linked to the website. So I probably do need to fix that. So what we're going to be taking a look at is in here, if you go to the benchmark folder, we have a number of different benchmarks. I'm going to be running some of these. These are our benchmark.net benchmarks. These are allowing us to go ahead and measure things like our memory footprint, garbage collection generation, all that stuff. This remote ping pong benchmark right here is what we call macro benchmark, where we're taking several different features that are all part of the Akka.net system, and we're testing the effects they have on each other together. Now, the one thing that kind of blows about this benchmark is that the way it's currently implemented, you have kind of like a three-body problem to some extent, where because we have two different actor systems that are running in the same process, they're actually competing for the same resources. They're using the same thread pool, even though they're using a socket to go ahead and communicate with each other. We have another version of this benchmark where we actually go ahead and host all this stuff inside its own process so we can avoid that problem, and it's a little bit easier to kind of measure what the real inter-process communication performance looks like. But this is what we've historically used for 6-7 years. So it's kind of its role in the course of the Akka.net project is kind of meant to be a signal for whether or not our changes to the software we made this version are better than what we had in the previous version. That's kind of what we're trying to go for. So I wanted to go ahead and show what our results were from the work we did last time on the read side. And here we go. So using the same machine, this is so the machine I'm running on is an AMD first generation Ryzen chipset. And it's basically a high-performance gaming computer I built back in 2017, so it's about 4 years old now. But you can see here that our sort of performance numbers were kind of in the 170,000 range for these later iterations. These numbers right here are the total number of messages we have to send end-to-end over one Akka.net remote connection. So these are all, let's say, multiples of a million. This number right here determines the number of unique actors that are doing this back and forth. And so as that number grows, the system tends to be able to do more things in parallel. So this benchmark is usually the most interesting. It's measuring how quickly two actors, one on either side of the connection, can successfully interchange 200,000 messages with each other. And so that message per second bit rate ended up being about 85,000. Over the course of, let's say, took about 2,350 milliseconds. Well, with these changes we implemented, you can see the aggregate performance of the whole system definitely improved to about an average of 180,000 messages a second. But this is the most noticeable improvement here. We dramatically sped up how quickly we could go ahead and deserialize those messages that were going back and forth to a single actor. So those little micro benchmark changes that we were making right here, these are the numbers we were taking a look at on Tuesday, really added up to a pretty significant performance improvement. So that's one of the things I'm very excited about. And this will go ahead and provide our end users with a whole bunch of free, we call it free lunch, where basically they get a faster piece of software without having to do anything themselves. Because none of these changes are breaking. That's what we're kind of working on ensuring in our quality assurance process, and it should all help the system really go a lot faster. Now, one other little benchmark related item I wanted to talk about before I actually start coding, just because this came up today. So this is, I believe, the final day of Microsoft's Build conference, and one of the little memes that emerged today was Microsoft talking about how .NET Core is now up to 10 times faster than Node.js. So I decided I wanted to go ahead and take a look at some of that data myself. This is the Tech and Power benchmarks. So this is my own Twitter account here, and I went ahead and took a look. I'm and this is true, I generally am pretty skeptical of benchmark claims, particularly when benchmarks are trying to draw a comparison between two different products. And the reason why is the temptation to go ahead and scum those numbers, meaning you do things that a real user wouldn't do, is very high, so you can claim you got a better number. I've seen some vendors and some open source projects pull off some amazing bullshit to try to go ahead and get a better benchmark number. So I was originally very happy with this. I thought, wow, these numbers look amazing. And if I go ahead and pull this up here, these are the actual Tech and Power benchmark numbers. So if you take a look down here, I have a bunch of different little filters set, but this is basically the fortunes query, which I believe performs a real database query that is not cached and is basically trying to go ahead and introduce a little bit of dynamism into this whole system. So the frameworks that want up here, are ones I've never really heard of, like Drogon, Juby, BeetleX, and BeetleX we'll talk about in a second, because that turned out to be kind of interesting. BeetleX is actually built on top of .NET Core. But ASP.NET ended up finishing in like the top 40. So this one right here. And then Zebra and Giraffe are also .NET web server applications, but they're written primarily, I think they're both F#, but they're built on top of Kestrel, which is the same engine that ASP.NET uses. So I was so impressed with these numbers. I thought it was great. ASP.NET didn't even show up on these, 5 years ago. It was just not that performant by comparison. So now that the Microsoft developers are advertising that it's up to 10 times faster than Node.js, I thought this seemed really exciting. Up until Bartosz. Here's BeetleX, which I'll go ahead and talk about in a minute. This is Bartosz, and I'm gonna butcher his last name. We'll say Adam Chesky. He is one of these low-level .NET performance experts. He's looking at things like, the disassembled, like IL from all these assemblies and stuff. So he's the sort of person who's smart enough to work at that level of the .NET stack. I am not, so I implicitly trust people like him because of the research they do. But he pointed out, check out the source for the C# benchmark. I normally don't write my own string, HTTP connection, and compiler-generated JSON parser when I'm building a web application. So after he pointed that out, I thought, well, he's probably right. So he went ahead and sent me a link to the source code, and I started digging into it. And this is what I wanted to pull up. So this is from the ASP.NET platform benchmark for Tech and Power. So this is one of the classes I just thought was absolutely unbelievable when I started looking at this. This is an ASCII2 string implemented as a stack allocated type. Meaning that normally when you're allocating strings that you're going to try to serve over an HTTP response, you're using a Unicode heap allocated string. This is what we spent all of last Tuesday trying to get rid of in our code, was trying to allocate fewer of these than what we had last time. So in this benchmark, let's go ahead and take a look at it. Let's pull up program.cs here. Actually, no, where was it? Maybe it was startup.cs. Let's take a look at it. Let's see. Benchmark.application JSON. Yeah, let's take a look at benchmark application. That's the shit. Let's pull that up. All right, so partial class. So they've got a couple of different benchmarks they have to do as part of Tech and Power. Some of them involve serving up plain text. Some involve database queries. Some involve doing things like parsing JSON. All of the strings they use for serving up HTTP responses are these custom stack allocated, constant strings. And so I'm looking at this and I'm thinking, this is absolutely not how a normal human would go about writing a ASP.NET application. No one would do this unless they were trying to win a benchmark. So this is the first thing I saw here where I was just like, man, this is total bullshit. That's unrealistic. And some of the other things Bartosz said about, I don't know, custom JSON parsing and parsing headers by hand and this sort of stuff. So what's the value of a benchmark where the developers who are running it aren't actually doing something that a real world user would do? And the answer is to look good in comparison to other technologies. And in the case of Microsoft, they want to attract people who might otherwise look at a platform like Node.js for performance reasons by being able to put this sort of meme out there about being 10 times faster. Now, I'm sure the intentions behind this are all good, but this is just not a real benchmark. In my opinion, if I go and take a look at this ping pong benchmark that we were talking about, now I mentioned one of the problems with it. Let me go and pull up Visual Studio here. I mentioned, let me go ahead and clear my screen, actually. I'll go ahead and close all my tabs. And let me go ahead and grab the type we're going to spend a little bit of time working on, which is, actually, I'll grab the unit test for that type, which are right here, in case I break something again. And I'll go ahead and grab our... Let's see, this is the wrong class. I'll go ahead and grab our actor path again. I just want to go ahead and do a little comparison between a benchmark that I think is fair and this. And then let me go ahead and grab one last thing I'm going to need for later, is our little span hacks class, which has been growing since our last stream. All right. So these are the things we're going to be working on benchmarking tonight and trying to improve the performance on. Let's take a look at the remote ping pong benchmark. Okay. So we go ahead and we create some protocol classes here. These are just all of our little standard messages for being able to go ahead and run this benchmark, gather some results. We're going to go ahead and try to print out some data about our environment that we're running this on. And then if I scroll down here, we're going to go ahead and return a little task. I'm going to go ahead and invoke this little function, blah, blah, blah. One thing we're doing, by the way, this might be considered cheating, possibly. One thing we're doing is we're setting the priority class of this process to high. So this means that when my benchmark application is running, this is going to be running with an elevated scheduling priority on the Windows operating system or the Linux operating system scheduler. I feel like this is actually fine because what I'm actually trying to measure is the performance of basically all of the Akadana infrastructure, and I don't necessarily want my benchmark competing with things like my web browser or my IDE in the background. This basically makes sure that that process gets to some degree priority. In a real benchmarking environment where I'm not benchmarking it on my developer machine, I'd probably be using a dedicated server that doesn't have anything else running on it, at which point this priority class wouldn't have as much of an impact. So that's why I don't really feel like that matters as much. This is kind of more of a problem for developer machines, to be honest. Now, when we actually start the benchmark, I'm going to go ahead and grab some client settings here, which is basically just the number of actors we have to start and the number of responses they have to go and produce. So I'll go to this little method down here. So I'm going to create 2 actor systems. We're going to go ahead and create and destroy the actor systems each time we do a benchmark iteration. Reason is we don't want these actor systems benefiting from caching from the previous round, because that would skew the results. So we want the results to be fair because we want to try to set a realistic measure of how much work the work we did paid off. This benchmark is for us primarily. It's like for the users of Akka.net. And so I go ahead and I create a little all started actor down here. I grab the addresses of both actor systems. Long story short, I go ahead and I basically make sure for each of the clients that's going to be participating in this benchmark, I go ahead and make sure that each client gets introduced with the other actor it's going to be talking to on the other side of the network. I'm not going to go into detail on all that code, but that's basically what's happening here. And then I go ahead and I tell the all can start actor, all right, as far as you know, is everyone able to start? Please let me know within 10 seconds of receiving this message. If that comes back and everything appears to be in good shape, then we're going to go ahead and actually run the benchmark now. And I do that by starting a stopwatch here. I go ahead and I tell all the receivers, I basically give them 50 messages each, and those receivers will continue until they hit that pre-allocated number. I think it's 200,000 messages per receiver pair. So I give them a sequence of 50. So they're going to go ahead and start streaming these responses back and forth to each other. And then I go ahead and just compose all these tasks together. I go ahead and wait for them to complete. Once they do, I turn the stopwatch off shut the actor systems down, and I report on the results. So this benchmark, in my opinion, is fair in the sense that I'm not using any special code or infrastructure that is other than what the default stock parts are of Akka.net. Our configuration, if I take a look up here, the only thing that's custom at all in our configuration is we basically set the logging level to error. That way we don't get a ton of logs and throwing off that data table there. So that's kind of really the only thing we did. Otherwise, these are pretty much the default settings. And then the last thing we're doing that I should mention for this benchmark, because it is relevant, is the messages we're sending back and forth between these actors. So this one, we're just echoing back whatever we receive. But the benchmark actor down here, I think we're sending, actually, you know what? They're all using totally untyped messages, so I can't tell off the top of my head. But I believe if I scroll here to where we prime it, okay, this is the message that we're sending. It's a string. So strings in Akka.net do not use the default object serializer. So we're not using reflection or JSON.net. We're just doing string encoding to do that. So one piece of overhead we're removing from the benchmark is we're removing the overhead, whatever the default serializer is. And that would be JSON.net. So using JSON.net to serialize this stuff would add a noticeable degree of performance overhead to this benchmark. And that's because it's using reflection on both sides of the wire. So we wanted to go ahead and measure basically the performance of the remoting pipeline itself, not the choice of serializer that's being used, and kind of basically go ahead and use that as our measure here. So that's the only other kind of custom thing we're doing, is we're serializing strings rather than objects. But otherwise, that's basically a fairly neutral benchmark. Doing stuff like this, where you're going and essentially running with code that users aren't going to have access to, or you're using custom data types that replace a built-in primitive in the .NET runtime, is a little janky. And so I don't blame Bartosz and some of the others who are complaining. I don't blame them for pointing out that this benchmark number is something worth being a little skeptical about. And this often shows up when you're trying to go ahead and compete against other technologies. Now, the one, I didn't take a look at their benchmark, but the one project I wanted to give a shout out to, and I'm going to go ahead and drop a link to this in chat. I had never heard of this framework before, but BeetleX, this finished in the top 10 of all the benchmarks there. And these are some .NET developers out of China, and they've gone and built basically a high performance HTTP, and it looks like it says remote interface. I don't know if that means gRPC. It looks like it's not. It looks like it says XRPC down here. Let's take a look at that. Beetle to XRPC. All right, I have no idea what XRPC is, but want to give these guys a shout out. Looks like they built a very high performance project. It can apparently outperform ASP.NET. I don't really have a use case where I need to use anything like this anytime soon. I'm not doing a lot of high performance web stuff. Everything tends to be a little bit more low level around here, but this is pretty cool. I would definitely love to get some feedback from people who've tried it, and let me know how it goes. All right. Well, with all of that out of the way, let's go ahead and actually dive in to going and doing some actual performance optimization. Now, the last thing I want to try to do before we dive in to doing the right side, here we go, is I want to go ahead and have a chance to clean up my pull request here and get this merged in. That way, all of let's say the performance benefits of my read side optimization can all get safely merged into Akka.net, and I can go ahead and start with all that code already in the code base. So any additional performance gains that we yield by building on top of the work we did Tuesday, I can go ahead and measure those separately. Otherwise, it's kind of difficult looking at those macro benchmarks to figure out what's the combination of my 2 nights of effort on this. So the feedback that I was given, I need to implement, is I believe we had some bugs with our IPv6 parsing, which I already fixed earlier this week. But this is Andrew. He uses Akka.net in a high-performance system at his company, which shall remain nameless. But they are a fairly big financial company in North America. And he basically went ahead and gave me a review. Gregorius on our team gave me a review as well. And he found a couple cases where we're not handling things 100%. So the first was our code for checking for IPv6 is a little sketchy. So I need to go ahead and make sure we don't accidentally misdetect an IPv6 address. So what I'm going to do is grab my link pad from last night. And by the way, one other thing I wanted to mention is I took my little span hex class. Let me grab this. I went ahead and I updated this earlier today, the latest version of it. This has all of our newest sort of code for backporting some of these features to .NET Standard 2.0. Although one thing I'm missing is I actually added, see if I can grab this. I wanted to remove one more allocation from our address parsing on Tuesday night, which was, let me find it. Here we go. The scheme has to be converted to lowercase. That's one of the URI requirements. And it's actually, that's defined in an RFC. But it has to be converted to lowercase. And so originally we had to go and allocate a string and then convert that to lowercase. So we're allocating 2 strings to do it. Well, I came up with a way of using spans to do this without having to actually allocate any additional objects in the heap. This was also Andrew's suggestion, I should point out. So the way this works is we're using the new stack alloc keyword. This allows us to put reference types potentially on the stack. It's primarily for allocating things like arrays of bytes or characters. So I took my input, I went ahead and calculated the length of that, allocated that into a span. This is a mutable span right here, so I can actually change its values. Then I just iterate through the array and I call, char.toLower invariant input. Then just convert the output to a string at the end. I haven't benchmarked this independently, but it actually didn't make a noticeable difference at all in the amount of bytes or the throughput of our bigger function we called it in. So it might have not been a significant amount of performance impact in the first place. So is what it is. Now, to go ahead and take a look at some of the feedback that Andrew gave me, the first thing he wanted to take a look at was, he said this was potentially unsafe. If we're missing a double slash, this might very well crash. So if I go ahead and let's go ahead and create some bad input right here. We'll go ahead and say no slash will crash. Akka.tcp foo at localhost 18884. Yeah, it's fine. So I go ahead and I run this little bit of code down here. Let's see. Is valid URI. Looks like it didn't crash. So that's not a bad thing. Oh, you know what? I see what he suggested. If I get rid of that, it should crash. Nope, didn't crash either. My code is more robust than he gave me credit for. Alright, under what situation could that crash, though? Well, let me go ahead and let's see. Let me go ahead and comment all this out. Alright, let's comment that out. And let me go ahead and go to my try parse address method. Let's see what's going on here. Spanified. All right. So Spanified, it still has foo in it. So do I leave too many characters there? I sure did. Okay. Explains that. So nope, Andrew as usual, probably right. Let's run that. Yep, okay, index out of bounds. That's what we want to avoid. So that was one of the points of feedback Andrew gave me. And he suggested I could go about fixing that. Yeah, there we go. I'm just going to steal his work. We're on the same team. Why not? Booyah. Alright. Well, that worked. So that's the first problem solved. And then for the slice, maybe do a length check with the scheme check. Let's see. First column position +1. I don't think the slice was actually the problem. Let's try. Like, for instance, if I go ahead, this is what's kind of fun about some of these n+1 problems. If I get rid of the colon altogether and I run it, it still works. The reason why is because I'm adding 1 to the end of that first column position. And so if that first column position is -1, well, actually we short circuit right there. So yeah, I don't even need to check that either. All right. So it looks like that appears to be working fine. Okay. So no damage there. Man, that wheated bourbon is freaking awesome. All right. Now, what was the other bit of feedback he gave me? We discussed this. Relative URLs actually can't be parsed by the actor path system. And I gave a technical explanation for that down below. Let's see. Do we have any additional guarding around blah, blah, blah being contained in a path? Well, paths aren't valid if they're in there, but he is right that we should try to defensively check for that. So, let's see. Pre-check for the slash in the path, and then math based off that index. Okay. So we want to go ahead and make sure that our IPv4 parsing doesn't catch fire and explode here. Although, you know what? His suggestion won't quite work either, because now I don't expect you would ever see this in an Akadana application, but it is a totally valid URI type. This is actually a valid, what's called an IPv4 mapped IPv6 address with a block notation on it. This is technically a valid address. I don't think we can bind to it on a socket in Akka.net, but that being said, looking for a slash isn't necessarily going to cut the mustard here. So what I really need to look for is I need to go ahead and double check. Let's see. If open bracket is greater than -1 and close bracket is greater than open bracket. So what this does is basically it validates that there is indeed a close bracket. Does validate that there is indeed a close bracket. Now for parsing the address, it's possible there may not necessarily be a path after this either. We don't have to have a trailing slash. Like if I scroll up here, this is actually a valid address. So I can't really check for, actually, this is a valid address. There we go. So I can't really check for a valid path after that. What I should look for though, is we absolutely do, if we have an address, we have to have a port. So I should go ahead and check to make sure that after we do this, close bracket's greater than open bracket. I need to go ahead and see, well, you know, if there isn't a port there, I actually think the rest of this is probably okay. I think now that we fixed that array out of bounds issue, I actually don't think there's anything that could come up that'll blow this up. We basically cover a lot of this. So I'm going to go ahead and take this little fix that Andrew suggested. I'm going to drop that into, let's see, parse address. Yep. I'm going to go ahead. Actually, let me check one more thing in GitHub here. Yes, all right. I do have one more little thing I added since I looked at this last, and I'll pull that up in just a moment. Okay. So this should resolve Andrew's bug that he found in my code. So that should take care of that. Yep. Yep, that looks good. The last little thing I did was I took note of, let me see if I can find this in here. Let's see, I think it's called frag lock. Let's see if I can find this. Okay, great. So, one other thing I forgot to do is we were not checking to see explicitly if there is a UID attached to this actor path or not. And if we don't have one, we can ignore it. But if we do have one, we should parse it into an integer and then pass that along into the actor path. That's going to make the overall speed of this method a little bit slower because we're allocating some more objects. But you know what? That's just how it goes. We have to go ahead and make sure we're doing the technically right thing. Now, the fact that our test suite passed without us doing that is, nice indeed, but we shouldn't rely on that. So let me go ahead and let's see, next slash, do all that stuff. Okay, looks like my code from earlier is still here. So I'm going to go ahead and I'm going to commit this. I'm going to go ahead and say, okay. Completed work on actor path. Now this pull request has already been approved for being merged in, but I still need to go ahead and give it a chance to run in our CI system. So I'm going to push that real fast. Actually, you know what else I'm going to do? I'm going to discard those changes. I'm going to go ahead and squash all this. Get rebase up. Okay. I'm going to go ahead and squash all these down. This will make it easy for me to do another little local branch that is going to benefit from having this code sitting inside of it. Man, chat, you are quiet tonight. Other than him, Jay. That's okay. Maybe it's the chill music. Maybe it's being past the middle of the week. Any number of things. All right. They should add a cricket emoji if there isn't one. All right. And I'm going to go ahead and just delete. I'm going to delete all these. Yeah, let's do that. All right, it's good to me. Origin, perf, address bars, force. All right, this should make it easier for me to go ahead and start a new little branch. Oh, oops, wrong branch. Be response. Boom. All right, got that done. Now, let's go ahead. Take a look at my commit history. That looks good. Oh man, I accidentally, I think, merged my code with some of the stuff that's already in dev. Crap. Hopefully I didn't screw that up. Well, looks like I did, but I fixed it. Whoopsie daisy. Alright, we'll go ahead and let that run. I've got auto merge turned on. This is probably going to be something racy in our test suite that'll fail, but that's alright. Not the end of the world. Now, let's go ahead and create a new branch. Perf, we'll go ahead and call this actor path serialized. Now, let's go ahead and set a brand new performance baseline. And we'll go ahead and start by running the actor path benchmarks. So this is how I sort of start, by getting my before and after numbers. All right. Okay, let's go ahead and do the path benchmarks. Let's see, and that'll kick off in the background there. All right. Let's see, we're in the ballpark of under 600 nanoseconds per operation, just about. But I probably added a little bit of overhead with some of those changes there. Now let me get rid of this, get rid of that. Now this will probably, oh shit. Yeah, I gotta start that over. Doing all that stuff in the background. I can even see it spike the numbers there. Let me go ahead and rerun that. Shouldn't have done a whole bunch of heavy-duty Visual Studio stuff while that was running. Alright. Let's see. Go ahead and run that. Now, one thing I want to take a look at. So we're going to be looking at a couple things when it comes to trying to prove the right side here. It's not necessarily just throughput. We want to look at memory footprint too. So let's take a look at the spawn actor benchmark. Now, is this measuring... What's the configuration here? Okay, it's measuring memory. That's good. We'll go ahead and run this one next. This will give us an idea of what our performance baseline is. Oh, excuse me. So we'll go ahead and take a look at that. Now, let me take a look at some of the other classes I've got to worry about. Let's take a look at address. Okay. Now, one of the things I've thought needs to die inside this bit of code we're going to take a look at is the address here. Now, not necessarily the address, excuse me. It's really this lazy to string. I think the memory overhead of having this floating around is pretty high. So I want to go ahead and take a look at potentially pruning that out of the system. So those benchmarks should wrap up in just a minute. So I'll go ahead and let that roll here. Once that's done, we're going to go ahead and start making some of our changes. But I think I want to go ahead and try getting rid of this lazy little block of syntax here. I know why we have it, but I don't necessarily think that's good. Yeah. Probably get rid of that. I can probably pool our string builders. That's another thing I can potentially do. So that'd be another area where we can potentially achieve some boost here. Then if I take a look at actor path, there's some pretty nasty crap that happens inside here. So for instance, this join method gets called every single time. We have to go ahead and stringify our actor path. And the way this works is it works by walking up the tree of actors and dynamically constructs a string that way. I think we could probably speed this up. Like I can see an opportunity right here to use stack along, for instance. That might be something we try. So that might be worth giving a shot. Okay, benchmark data. Still working. All right. Let's go ahead and get started. I'll go ahead and do stack a lock. This. We'll go ahead and call this. Next. Int offset equals buffer.length. E.name copy to. So for each one, so what he's doing is he's using some buffer copying behind the scenes here to the underlying memory. And I think they're working backwards. Yeah, so they're working kind of backwards to the array here. Okay. Well, I can go ahead and say, let's see. Buffer. Copy to. Okay. Why don't we go ahead and do this? E.name. Copy to. I go and say my destination. Let's see. Does this not offer any of this? No, I definitely do not want to run a build. All right, here we go. Final benchmark numbers. Looks like actorpath.parse is at 672 nanoseconds now as a result of some of those changes. So I got to go ahead and grab that. Let's see. I think this is it. Yep. Okay. Looks like this already failed. Let's take a look at why that is. Okay, Linux for some reason just randomly, intermittently fails in Azure pipelines. Like it fails during the download, .NET Core tool stage. Mostly from...
Nobody cares these days, and it's a damn shame.
There might be a more efficient way of doing that. Anyway. Actually, you know what? Maybe there is a more efficient way of doing that. We could go ahead and check that character every single segment we're looking at. Well, I won't worry about that for now. But we'll go ahead and stick with these numbers. Alright. Let's go ahead and take a look at this instead. Copy to buffer destination link. Okay. Looks like the copy to method here doesn't really have a huge amount of, let's say, overloads working with spans. Let's go ahead and give this a try. Let me go ahead and leave the original code back in place. All right. So leave the original code there. Clear that. Okay. We can try to fake it. Or... in fact, you know what I'm going to do? E.name. Span. I wonder if I can do, yeah, for var I equals 0, I is less than spanified. Length I plus plus. I don't like doing nested loops if I can help it, but I think it probably won't kill me in this case. Okay, there we go. That's better. All right. So I'll go ahead and say, and then our offset at the end here is that we're basically kind of working backwards. So I'll go ahead and say buffer I. Now, what happened to this? Oh, I see. I think there's another extra character down there. All right, there we go. It's more like it. Buffer offset. I wonder if there's a way I can do that. Nah, I didn't think so. All right. Don't need a semicolon there either. Buffer offset equals spanified. And then I'll go ahead and say offset 1. All right. Then at the very end, once we're all done, I'll go ahead and return buffer string. I think that should be all right. Oh, loop control variables never change inside the loop. Well, that would be a problem, wouldn't it? It would be an infinite loop there. So I'll go back here. Need to do p equals p.parent. Yes. Okay. And we'll give that a try. We'll wrap it. Do a little bit of resharpening here. Okay, perfect. Interesting. So we go ahead and we compute the entire length of the string in advance. So we actually iterate twice. Wonder if that's necessary. Well, I guess we'll find out. Okay. So the numbers we want to take a look at now are the two string values here. How much can we speed up our actual string serialization process? So let's go ahead and give that a try. And I'll also go ahead and work on, while it's running, let me go ahead and wait for it to compile. That way I can do my work in peace. Let's go ahead and do active path benchmarks. All right. That should be running now. Now let me go ahead and take a look at this. Lock is spanified the index of. You know, I could get rid of this. Yeah, why don't we give this a shot? Let's see. Next slash less than zeros. Spanified at length. Final segment. If spanified fragment index for hash here. Greater than -1. We'll go ahead and say fragment equals spanify.slice, and we'll go ahead and say start a frag lock. Yeah, I'll do that. Frag value will be ban hacks dot. What do I do down here? Parse. Fragment. Guess I don't even need to declare that up there either. I can move it to a lower scope. Frag value is that. And then set vector path. This is spanified slice 0 frag value. Oh, no, that should be frag lock. Can I use local variable spanified before it's declared? Oh, derp. That's what I did wrong. Okay. Spanified slice. I'll go ahead and do this. That way we're only allocating that final actor path once. Child actor path. There we go. That should do it. I think that should help with our performance too, and I can get rid of that. Perfect. Yeah, that should do it. All right. Woof. Exception has been thrown by the target of invocation. All right, well, whatever I was trying to do before there with the actor path.join method went down in flames. That's no good. Let's see. That was the join method, I believe. All right, yeah, there we go. Okay, we'll tell you what. Let me go ahead. Let's see. Let me go ahead and start a new link pad script for this. this into a little C# program. And let's see. I'll move the void method in there later. Static class. We'll call this, yeah, active path formatter. All right, and public string join path actor path key. I got to install a NuGet package to make this work. All right. Let's get rid of that. Make this static. We'll go ahead and call this active path. And then get rid of that. Next, you need to go ahead and reference some NuGet packages. Add to query. That's the one I want. Perfect. Move this back in here. Close. Let's go and do address.parse. Aka. TCP. We'll go ahead and call this Twitch at HimJ27. Alright, go ahead and give you a shout out there. Let's see, that's my actor address, actually. Alright, and then we'll go ahead and do path equals root actor path, actor address, user, who, bar, as. Okay. And then I want to go ahead and do console.writeLine. Go ahead and copy this. Cannot declare instant members in a static class. All right. Have it your way. Well, it looks like that worked. Even though it probably shouldn't have. But it worked in the sense that it didn't throw an exception. That's definitely not the output we were going for. So we'll want to take a look at that. First, though, let me go ahead and grab the old code I had gotten rid of and put that back in place. I think this is it. Yeah. Yeah, I'm going to go ahead and grab that. Actually, I think this is the only thing I got rid of. Was that? Yeah, let me grab these two. Okay. Oops, new. That's the one. And then the other thing I got rid of. I should have used a separate commit for this, but I was being sloppy. Yeah, that's what I want. Add that back. That way I can go ahead and try to see if that read side optimization we just added back had any performance improvement or not without worrying about this thing exploding. All right. Go ahead and rerun that. Make sure our benchmark starts up. Then we'll go ahead and start the debugging process on our right side code. I look forward to a day when robots can do all of this. Although I'll probably be out of a job in the event that happens. Okay. That's looking better. Looks like we definitely got some of our performance gains back. Good. I might have to go ahead and cherry pick this out of that other branch. We'll see. But it looks like that's all running okay. Makes me feel happy. Alright. Now let's see what the hell is going on with this code and why it didn't work. Alright. Okay, well that seems like a problem. What the fuck? Sorry, apologies for the French, but it absolutely should. What is this new devilry? But long story short, path should be equal to a big complex path right here. Buffer offset. So one of the things that we overload in Akka.net is the slash operator. Oh god, is the slash operator using join under the covers? Well, that could certainly be a problem for me. I think it is. Let's take a look. In that case, I've got a much more serious problem, but I don't think we do that. This is what's called operator overloading. Yeah. That looks fine. Yeah, this all looks vanilla to me. Alright. Let me go ahead and call this child actor path. Alright. Are we modifying P anywhere? Is that part of the problem? Alright, let's take a look. Oh, yes, we are. That's my problem. Well, I'm an idiot. Okay. We're modifying P right here. That's part of our issue. So, I basically wasn't ever setting it back. All we needed to do is just make a copy. So, I'll go ahead and do var E for estimator equals P. That way we don't destroy our original copy. Okay, I thought I was going crazy for a minute. Alright. Okay, this looks okay. Okay. This is looking more like it. Alright, I can probably get rid of the breakpoints for now. Let's go and copy all this output. Oof. Index is outside of the bounds. Okay, well, I guess not all the way. Alright, let's go ahead and start this up. Buffer offset is 13. Total length. E.name.length plus 1. Okay. Total length is 17. Alright. Offset buffer dot length. Alright. Alright, so offset is 13. Then it's 6. And we're up to Baz, I think. Spanified Baz. Okay. My offset is -1. That's a bit of a problem. How did we get there? What does my buffer look like so far? I have a window I can go ahead and write this out to. I'm gonna give this a shot. Not performant, it'll help me debug. Go ahead and do buffer.slice 0 to offset. Alright. And let's see where we're at. Oh, gosh. Nope, I'm not a smart man. That's what we need to do. Need to slice the buffer right there. Okay. ZAB. We're doing things backwards, is what that looks like. Interesting. Yeah, okay, this is some pretty crappy code I've got implemented here so far. Alright, so we're gonna have to figure this out. So my problem is, so far, I appear to be transposing things in completely backwards. So I'm starting from... Yeah, okay. So this is a bit of an n+1 type error, again. Alright, I think I know what to do. So I need... Let's see. I need to go ahead and do, I think it's buffer. I'm just trying to think what's the right way to do this. So offset minus, what do you think? Man, this is nasty stuff. Spanify.length. Let's see. Plus I. Let's give that a try. That was even worse somehow. I basically need a block copy operation. I need to go ahead and transpose all of the bytes starting at offset. Then I want to go ahead and slap an array on here. We know offset minus p.name.length. I do that. You know what I can do? So I can go ahead and make the offset a relatively temporary thing. What if I go ahead and do offset? Okay, so this is having me actually start. I didn't even notice this part of the code. This is actually having me start at the front of where the little index is. So I need to go ahead, probably do this. Give that a try. Get rid of that. And then I'll go ahead and have, let's see, bar written bytes 0. I'll go ahead and say at the end here, written bytes plus 1, basic equals, plus equals 1 plus spanified. So each time I go ahead and I start, I should go ahead and say, all right, offset's going to start minus the number of written bits. I think that should do it. Index outside the bounds of the array. All right, let's take a look at this. Yep. Woof. That didn't work out. Let's see. There's something screwy going on here. Oh, it's because it's freaking negative as soon as I run it. God. Okay. You know what? I'm just going backwards here so far. Alright. Offset minus p.name.length plus 1. So we're basically moving from back towards the front. Okay. Alright. Temp offset. Let's do this. Far right offset. equals offset. We'll go ahead and do +1, so we can move past the slash. Actually, if I do this, get rid of the +1 there, that should do it. That's looking more like it. Yes. Beautiful. So if I get rid of all the breakpoints, what do we end up with? We get a fully joined path at the end here. Okay. Now we're in business. So it looks like so far I have managed to go ahead and bring back some of our performance on actorpath.parse. That makes me very happy. So we're going to go ahead and commit that change. Let's see, we're going to do a restore, parse performance, actorpath.parse. That looks great. Go ahead and commit that. Move my PPG window over to the right. All right. Now I'm going to go ahead and swing back to my other branch. Pick out perf. I think it's address parse. Get cherry pick perf. Let's see. So I basically just moved that commit onto my other branch. That way I can go ahead and factor that into that benchmark. And I'll grab this little value right here. So it's going to restart my build on the CI server all over again, but that's all right. Grab that. Great. Somehow, I've managed to already reduce the number of bytes pretty significantly. From 216 to 168. I have no idea how I did that. That's a mystery. So we'll figure that out. Let's take a look at what I committed, actually. Just calling buffer to string apparently did it. Not even just getting rid of the new string and doing that. I think it prevented an entire copy down there. Okay, that is hysterical. And yeah, Gen Zero garbage collection doesn't lie, folks. All right, that's okay. That is funny as hell. I gotta make a comment on this. Oh man. Oh god. Okay. Let's go down to here. Oh my god. That is pretty funny. I can't believe that. Okay. Alright, let me go back to... What branch was I just on? Actor path serialize. Okay, let's give that a shot. Don't want that. Gotta get rid of all those. Okay. Now I want to take my code from LinkPad here, and let's give this a try. So, one of the things we could probably do is get rid of this join method altogether, but I'm not feeling quite brave enough for that. Reason being is there's some important trade-offs with that, and we'll see that show up in our memory footprint comparison. So, let's see. Where's the stupid join method? Alright. Okay. Dear compiler gods, please be happy with thy humble servant. Code is heuristically unreachable. Ah, we already figured that out, didn't we? So you know what? We're gonna go ahead and do... Nope. Ah. Why not? I guess I gotta get rid of the declaration here. Alright. There we go. Now let's go ahead and run that benchmark again. And then I really need to be able to go ahead and do a memory benchmark is the next thing I want to do. I want to be able to go ahead and clock basically what the memory footprint of a bunch of spawned actors are. Let's take a look at this. This looks complicated. Well, it's not that complicated. Start test. You know what? Screw it. Pouring myself another bourbon. After being embarrassed by all of those N+1 errors, I need something to go ahead and maybe feel better about the state of my programming abilities. And alcohol is usually the easy answer. Yes, I think I have earned it. Thank you. Appreciate you saying as much. Okay. Oh my god, I'm an idiot. Okay, I forgot to actually start the benchmark. Alright. There we go. Yeah. We're going to call this the sloppy stream. Okay, so my performance before was around 580. Now I'm at 650 nanoseconds. What branch am I on? You know, this is bullshit. There's got to be something else in the background that's eating up some CPUs somewhere, because I actually haven't changed the code since I ran that benchmark last. Oh well. We'll see. Funnily enough, I actually got better performance numbers on my crappy, like, 10-year-old Intel machine than I did this Ryzen one. So I'm wondering if there's, like, some chipset issues, potentially, that causes Ryzen to differentiate from a lot of other x64 machines for doing benchmarks. But we'll find out. Alright. Oh, God. I forgot to get rid of, Hold on a second. Yeah, that would do it. Forgot to get rid of my logging statement that was in there. Alright, well. Try that again. That would definitely have a negative impact on performance, for the record. Alright. Let's go ahead. Get that back up and running. Okay. Alright, there we go. And now, for some reason, the performance is fine again. Even though we weren't using that join statement at all. I don't get it. Computers. Who really does? Who really gets them? Not programmers. Not us. Definitely not us. Alright. Okay. Now I want to see what the join performance was, so we'll go ahead and let that run. The string with UID. Doing an awful lot of string allocation. All over the place. The serialization format, append UID fragment to string with the breath. Man, the jams are pretty... Thank you, MJ. Appreciate that. The jams are going strong tonight. I'm digging the music. I normally pick a much more chill channel than this one. I'm glad I didn't. So here's what I think. We allocate a ton of new strings. I know we do one every single time we have to serialize. I'm thinking about caching that value and trying to measure the performance of that. Alright. So these are the numbers that are being produced by some of our stringification benchmarks. This tells me, based on just the data I'm seeing so far, that our changes probably didn't have much of an impact. So that's not necessarily great. Now, I mentioned that one of the things we need to do is do a benchmark of the memory footprint of actors. Here's the little bit of cost I have to kind of worry about. If I go and cache these values for the sake of throughput, I'm making the default memory footprint of Akadana actors higher. And for people who are running millions of actors inside their applications, caching these strings could potentially be really expensive. So I need to be a little mindful of that. So that's why I want to go ahead and do... All right, let's take a look. Benchmark numbers. Let's compare with what we have up here. Scroll down to the bottom here. Okay. Oh no. Why are these failing? Let me go back to full screen on this. RACI unit test that had nothing to do with me. This is Akadana persistence. We have a lot of RACI tests in our suite. It's a constant garbage collection exercise to keep them cleaned up. We spend a lot of time working on it too, but it is what it is. Okay, so I was looking for the performance numbers, and I wanted to compare them to what we just got. (205, 227, 258, 168 bytes. That's what we got last time. Okay, so that's one set of numbers. Yeah. So what do we have? 204, 227, 243. Margin of error 4.8, 2.2, 4 nanoseconds. So we basically had zero impact on the throughput here, but we did reduce the number of bytes allocated by about 8. So that's small potatoes, grand scheme of things. We didn't really do a whole lot to move the needle there. So that's a bit of a disappointment. Well, next benchmark I'm going to run is memory footprint. Let's see if we can go ahead and optimize that to some extent too. I'll do the address benchmarks first. Let me go ahead and take a commit here. Okay. All right, so we spanified that. Move that off screen here. Oops, typed that in wrong. All right. Publish that to GitHub. Whoa, those are some big numbers. What the hell are we actually even doing on that benchmark? Guess we'll find out. We might be doing tens of thousands of things under the covers there. Oh, never mind. Those aren't big numbers. What am I thinking of? This is the number of microseconds per operation there. Never mind. Ignore me. Okay. Let's go ahead and submit a new pull request. Alright, let's give that a shot. Oh, whoops. You know what I forgot to do? I need to convert this to a draft. Got to make that a draft pull request. Alright, I need to see some of these bits of the test suite pass down below here before I can get this merged in. It'll be a while yet. Alright. Let's take a look at this. What were our big expensive methods? Address.parse. Everything else wasn't so bad. Yeah, like, look at that. Address to string? That's tiny. That's good. So address.parse, if I'm not mistaken, is using that URI try parse stuff under the covers there. Yeah. How often does this get called? 71 times? Woof. Alright, let me see if this is in any high performance areas before I get too excited. Looks like it's a bunch of unit tests. Yeah. The remote deployer, yeah, no one cares. Split brain resolver. Cluster settings. These are all places that get infrequently called. So even though I could theoretically improve the performance of this code just by using exactly what we had from last night, I'd rather not bother. I think it's probably safe as is. Alright, let's take a look at the string method. Oh, it's because we're caching it. That's right. That's why toString is so fast. We go ahead and use a lazy value and we cache it once. Now, I believe these address values will get passed around somewhere. Let's go ahead and next, I want to go ahead and run these actor spawn benchmarks. Don't know why that's compiling. All right, let's go ahead and do some spawn actor benchmarks. Now, what we're trying to do here, I actually don't really care about the spawning throughput. It's not really a super relevant factor for me, and string parsing doesn't even happen there at all. What I do care about, though, is the memory footprint. One of the things that kind of sucks about building a framework that has lots and lots and lots of users is... Okay, I expect these workloads to actually take a while. These are actually fairly long-running benchmarks. But one of the things you have to worry about when you build a framework that has lots of users is the shapes and sizes of use cases run the gamut. So you've got people who have very narrow use cases where they're using Akka.NET in a very specific context, like they're running, I don't know, embedded devices with it, and they don't have very many actors. But then you've got some others who are running gigantic cloud deployments that have actors spread out across hundreds of processes. And you have to go ahead and worry about the memory footprint of, you know, having 1 million actors per processes in an actor system that has, well, in an Akka.NET cluster that has 100 million actors total, right? So I have to kind of worry about both of those. So it'd be very easy for me to kind of narrowly focus on throughput, which is the benchmark that most people tend to give the most credence to, and to say, well, we should just go ahead and cache these actor paths, etc. But if I do that without also paying attention to, let's say, what the actual impact is on total memory footprint, I could end up really pissing off a bunch of our users. So I want to be mindful of that. So that's why we're running this benchmark. All right. Actor spawn, on average, we spawned how many actors? We spawned 100,000 actors, and we allocated in the process 639 megabytes. Now, actors typically, in terms of their actual throughput, actual memory footprint, it's closer to about 1,000 bytes per actor, maybe 2,000 bytes per actor. But because we're in the process of churning them, where we create a bunch, kill them, we're sending messages back and forth, all that sort of jazz, the actual benchmark is going to go ahead and pick up some of that background noise too. So one of the things I actually don't really like about this is that number is so big that if I made a difference, like getting rid of the address, I don't know how much performance impact that would have. So, but you know what? I'm going to give this a try anyway. I'm going to get rid of that lazy. I'm going to go ahead and just refactor this. That stuff. I don't necessarily think we need a string builder here. I'm going to go ahead and just use an interpolated string instead, since we basically know what the structure of all this stuff is. So I'll go ahead and do, yeah, protocol, system, and then here's what we'll go ahead and do. We'll do tail equals both of these have to have a value in order for this to make any kind of sense. Okay. So both of those have a value. That should do that. I'll go ahead and do... I guess I'm over-optimizing this part, now that I think about it. That's okay. I like to be precise. We can't have an address without a port. That'd be... I don't think, anyway. Let me think about that. I don't think so. I don't think we can. I can't imagine a use case where we do. We certainly don't support it when we're parsing. If someone's using a custom transport, it doesn't work. I guess I'll find out. Do that. Okay. Now if I go down here, get rid of that. I'll say if string string equals create lazy to string. We don't care about thread safety here. If we go and allocate some extra strings, who cares? It's not the end of the world. We don't want to pre-allocate this address in case no one ever needs to serialize it. But we also don't want to be, you know, paranoid about accidentally doing this multiple times. I think this will be fine. And then lost my train of thought. Ah, there we go. All right. Okay, let's do that. And I don't want to necessarily... I'll run my actor spawn benchmark. Why not? We'll see if that has any impact at all. I doubt it, actually. Actually, no, let me do my address benchmarks first. Start with the micro, then work to the macro. Alright. That's off and running. Next, actor path. So where does our join method get called? When we call it to string, we've got to do serialization format. The string with UID, when do you get called? Only in one spot. Okay. A lot of different little operands in here. Ugh. So we're mutating our last set of elements here every time we do this. That's dirty. Serialization format. Append UID fragment to string with address. Right. The string with address is that. Yeah. And so to string is calling what exactly? You know, you should just go ahead and really call the string with address. That's basically what you're doing anyway. Now we have some dry principal stuff working in our favor there. Alright, now how often does this get called? This is the one I care about. Serialization format. Okay, the remote PDU codec. Every time we have to serialize an actor reference, which is frequently, we have to go ahead and convert this to serialization format with address. String with address, append UID fragment. So we do this if actor path address host is null. We do deserialization format. Alright, this might be something we want to think about caching potentially. This is still running. So I'm willing to go ahead and entertain doing that. Now we have another set of benchmarks we're going to run. Oh, what's going on here? Doesn't look good to me. Got a bunch of multi-node tests failing. We just fixed these today, so this would be new information for our test suite so far. Well, the cluster sharding system is not happy with how we're doing stuff. So I wonder if that means I broke some of our tests in there, which is very possible. I did that before. So I have to go ahead and dig through our test suite, manage some of that, but that's okay. One of the other things I want to do before we sign off for tonight, so we've only got about 10 minutes here. So I have another benchmarking tool that we use for these macro benchmarks. I wrote this one myself, nbench. And I need to go ahead and grab my instructions here. Right. I want to go ahead and run, I think my actor memory footprint benchmark is actually more accurate than benchmark.net. So I want to run it. And that is inside akka.test.performance actor memory footprint spec. Alright, well, address to string. Looking pretty dang good. 1.4 nanoseconds. I'll take it. Let me go ahead and upload that. Check all that. Alright, we'll go ahead and commit that. we're able to go ahead and get rid of a very expensive, ugly-looking class that I hate from the code base. That makes me feel warm and fuzzy. Go ahead and discard all those changes. Get rid of all that junk. Alright, so I'm going to go ahead. Actually, you know what? I'll open up a brand new PowerShell for this. Let's go ahead and switch to repositories. This Okta.net. .NET run, C release. Then I've got to pass in some of these NBench parameters. And the parameters I want is I want concurrent enabled. And I want to go ahead and just include something like this. That sounds good. All right. I'll go ahead and do, yeah, dash concurrent through include like that. And what was my class name? Actor memory footprint spec. All right. Go ahead and kick this off. NBench does not have nearly as nice of a experience as benchmark.net does in terms of its the experience of actually going and working with it. Now, this is using the garbage collector to go ahead and measure memory. Ah, crap. You know what else I forgot to do? I'm not actually storing the values correctly. Let me go ahead and grab... Is this Okta.net? No, it's not. Grab this. I need to take a look at our build script real fast. And this is what I want. Output. Let's run this one more time. Output, and that should be in. Go ahead and close some of that down. All right. Let's see. I want to go ahead and grab the Okta.net folder here. And I usually stick all this stuff in perf results. That's where I like to put it. Let's do that. Put that away. So yeah, so these numbers are kind of jumping around a little bit because we're measuring memory allocation based on the page file. So, but we're running this enough times so we should get a rough idea of what the actual performance impact is. Okay. And if I take a look in Visual Studio, or VS Code, excuse me. If I take a look in our perf results folder, which should be up at the top here. Get rid of docs, perf results, here we go. All right, receive actor. So let's see. On average, total bytes allocated. Those are the per second totals. We allocated about 80 megabytes worth of data to go ahead and allocate 10,000 actors. That's, let's see, 80 megabytes of data. Actually, no, that's the maximum, excuse me. Average was 61. That's quite a lot, actually. So if I go ahead and, let's see, check our status here. All right, let's go ahead and check out the development branch. Run that same benchmark all over again, see where we're at. Yeah, see, I'm getting values like 18 megabytes and stuff like that. I think these numbers aren't very good. Maybe I need to create a better benchmark for measuring this. Probably wouldn't be a bad idea. Yeah, average allocated again, about 80, yeah, 56 megs. So if I divide that by 10,000, it's 5 megs per actor. That's ridiculous. We definitely don't do that. So I don't think I've run these benchmarks since .NET Core 3.1 came out for actor memory footprint, so it's been a while. Why don't I do this? Okay, another new branch. Get checked out. B benchmark actor memory footprint. We use benchmark.net. Go to spawn actor benchmark. We'll go ahead and call this. Go here. This will be actor memory footprint benchmark. And I want to go ahead and use here. Use that. Benchmark. Go ahead and do public. Oops. Public actor system. It's not what I wanted. Get rid of that. This is what I wanted. Go and do actor system upgrading. Actually, I'll go ahead and give this a nicer name. Then, and then clean up. There we go. I wonder if I can make this a task. Okay. All right, pretty much a bare bones actor. And the other thing I'm going to do, I'm going to go ahead and cache props up here as well. So I don't have to create those each time. So that overhead is not super interesting. All right, go ahead and do props. I'll go ahead and stick through on the stream tonight until the stream run, until this benchmark gets a chance to run. All right. All right. Let's give this a try. This will go ahead and allow us to measure the current memory footprint. Let's see. Let's go ahead and do 7 spawn actor benchmarks. .5 seconds per operation. That seems a little crazy. Unless it's jitting and destroying actor systems every time. Yeah, I'm not sure I like that number. Unless it's doing thousands of operations, in which case that would make a little bit more sense. But we can spawn actors at a rate of like... I mean, you saw in the previous benchmark that one that we ran that was all iteration based. We spawned like 100,000 actors in 2.5 seconds, which is about right. Last clocked performance for this was about 100,000 per second. Oh god, did I run? I ran the same benchmark I did from before. Jeez, okay. Man, I'm all over the place. Alright. Let's give that another try. So yes, that was 100,000 seconds to spawn an actor. So now it looks like, based on the workload pilot, looks like it's about 21 microseconds per operation. That sounds more like it. Yeah, 21 microseconds per operation. So if you're doing about 50,000 a second, yeah, 20 microseconds is about right. I feel very disturbed by the fact that I broke the build, apparently, with my most recent change. Well, it's possible, because I know I had to fix a bunch of errors before, where it wasn't working quite right either. This is on the actor path parsing side of things, so I might have to spend some time after the stream's over tonight working on that. And we're in overtime right now. Yeah, I wonder actually. I'll let that run for a second. Let's get back in here. Oh, this is on the dev branch. Well, no wonder. All right. That's still going. So what I'm going to do... Actually, I need to add a copyright header before I can even commit this. Let me do that. Add a copyright header. Get this all checked in with the project proper. Actor. There we go. Let's see. Yeah. Added dedicated footprint for measuring actor memory footprint. Wonder how many of these it's going to do. Well, I've reached my maximum bourbon threshold for debugging, so I don't think I can actually push that any harder than I have so far. But this should be done in just a second. Then we can go ahead and call it a night here. My guess is what benchmark.net's doing is it's noticing a bunch of outliers in this performance band right here, if I go and highlight it. And it's trying to go ahead and produce a smooth curve by just increasing the number of samples that it's taking. This Akka.NET code is asynchronous, so those numbers could be all over the place. That's kind of the nature of the beast. And I don't know if it's necessarily prioritizing the process or doing anything else to try to smooth out those numbers, so it very well might be at this for a while. Well, I'm going to go ahead and commit this so I can go back to trying to fix some of the other stuff. Yeah, let me go and just commit this. Put that there. that on up. Okay. Go back over here. I gotta figure out what went wrong. Let's see. Merge that in. This is a pretty simplistic benchmark, so I'm pretty sure I don't need to clear that with a team. So I'll go ahead and just put auto merge on that one. That'll merge itself in on its own. A relatively short period of time here. Let's take a look at what went wrong here. Man, what is this thing gonna give up? Jeez. Trying to gather a lot of samples. Alright, well, I definitely broke something. So let's take a look. 92 failed tests. Okay, well, I probably got too clever for my own good. So let me go ahead and check this out. I dealt with this the other day. It's definitely, I mean, goes without saying, I definitely screwed up the parsing code. Okay. Let's see. Okay. Join. I think it was the parse method here. Right parts, yeah. Alright. Show me where the damage happened. Let's go back to link pad. Yeah, I'm pretty sure it was all this stuff. Oh, try parse address. Derp. Actually, no, that part seems fine. Try parse address looked like it worked. No problem. It's, pretty sure it's this part. That's what's screwed up. If frag lock is greater than -1. Active path equals new child active path. Spanified to string active path value. Oh, I've got an easy way of testing that. Man, these jams are good tonight. This is getting a very 2005 vibe. Okay, what the hell is going on with this? How is this thing still running? I'm gonna have to tell benchmark.net to cut it out. It's like, dude, just I think 50 runs is probably okay. I mean, we'll stick around for a couple more minutes. I'm not gonna hold my breath on any of that. A test failed. Okay, well that would be a problem, yeah. I think I found the source of our issue, which is that we're injecting all sorts of weird SHIT into the parsing process. Okay. So where did I do that? Well, I get trying to be clever. I'll always find this stuff. Why you rely on a good test suite. Spanified. I'm gonna set a breakpoint. Oh god, I might be an idiot. I think the problem is not here. Man, I didn't even get a chance to get that far. Alright, I want to see what's going on. Thanks, I'm glad you like it. I enjoy doing it. It always makes me laugh. Alright. Bourbon supplies have gotten critically low, though. Okay, what is going on here? Okay. Well, I figured out where one of the problems is in all this code. And it is, funnily enough, in our join command. This is actually a problem. I laughed and I thought I was a genius earlier. Nope. No. Nope. I screwed up. Alright. No, that was bad. Let me go ahead and rerun that. Problem is that actually I'm pretty sure all of our parsing worked fine, but I broke the join method. Okay, benchmark.net, this is not cool anymore. Yeah, you know what? Just give me a second. I'm turning auto merge off. Oh, crap, it's already merged. Okay. Well, I gotta go ahead and bring that down and fix it. So that's never gonna finish at this rate. Okay. Yeah, let's see. Fixed. Alright, let me go ahead and push that up. Okay. Alright, we've had enough. We've had enough of that. Let me go ahead and merge this down. I want these numbers before we sign off. Okay. Alright. We got that all squared away. Cap. Active spawn. Alright. Take a look in here. Active memory footprint benchmark. Let's take a look at the config real fast. And let's take a look at the config for active spawn benchmark while I'm at it. Alright. Yes, I do want that. Target count 30. Actually, you know what? We'll do 25. Okay. Go ahead and commit this. Ah, nope. Go away. Damn it. Alright, I need to get rid of that. That was the wrong branch. Get rid of that. Alright, branch D. This is what I want. Alright, let's go ahead and merge this one in. Man, what an idiot. Can't believe I was like, oh yeah, like, can't believe this is so much more efficient. And it completely breaks everything. Whoops. Alright. Let's give this a try. Alright, actor memory footprint benchmark. Don't let me down this time. It does happen. It's very true, him Jay. Update the branch on this pull request too. Alright, that should be going through. Good stuff. Alright. Four kilobits per actor. 68.22. Okay. I'll be your Huckleberry. Alright. And there's a way I can configure this. I'm trying to remember. That's how you do it. And I'm going to set this to 1,000. All right. Now, if we're allocating 4 kilobits per actor, we've got a problem. These are fat actors in this case. So we're going to have to go ahead and do a whole bunch of memory trimming. Which means I can't really afford to be very, how do I put this? I can't really afford to go ahead and cache a whole bunch of stuff in the name of throughput. It means I've actually got to look for ways to try to cut down memory consumption. But the one thing I guess I got going for me is that memory is relatively cheap. So we'll figure it out. Alright. So we allocated 6 megabytes with 1,000 actors. Okay, they want a bigger number. Alright. That's right. 1,000. Go ahead and do a million. Why not? Yeah, how about that? How about them apples? Alright. And this will be like, let's see. Memory footprint. So if each actor takes up a kilobyte each, million actors should be a gig of memory. Okay, I might have overdone it. Let's take a look at Task Manager. Alright. Well, something's eating up a shitload of memory, and it's, well, of course, it's Docker, but after that, I guess in like a distant second here. Okay, this is taking 26 seconds per iteration. I think we may have overshot our target here. So let me go ahead and drop this down to, rather than a million, let's do 100,000. Let's do that. Whoops. Yeah, I don't want to spend 10 minutes here waiting for benchmarks to run. Alright. So I have to buy an order of magnitude. So let's take about a minute to run. I'll let that fly. Hope I didn't turn on auto merge for that. Let's go ahead and commit that. That's still a little bit too slow for my taste. I want more instant feedback than that even. Alright. That's better. Alright. Let's run that. And we'll go and do active memory footprint benchmark. Well, we're definitely going into overtime tonight for sure. Alright, that's more like it. Okay. We're finally approaching something that resembles resolution here. Alright, good. Well, I do not mind the music. Alright, we getting the real numbers now? Yes, we are. Great. Give me those numbers. 70 megs for 10,000 actors. Okay. So. Let's look at a garbage collection. No Gen 2, but a bunch of Gen 0 and Gen 1. Okay. So. 70 million divided by 10,000. That is 7 megabytes back per memory per actor. That doesn't make it. Nope, got my sig figs wrong. Alright. There we go. Divided by 10,000. 7K per actor. Now that sounds pretty high to me, but that's within the realm of believability at least. So that's going to be something we're going to need to take a little look at, is whether or not we can go ahead and try to reduce that figure. But I'm going to go ahead and leave that as an exercise for next week sometime, or maybe I'll do it on my own. By the way, thank you all for joining me again tonight. I really appreciate it, and I'll go ahead and plan on seeing you all next Tuesday. Thank you very much, and have a good night.